to go over our quiz real quickly. Draw the orbital notation for an atom with 16 electrons. One thing that every year is a little bit of an issue for folks is remembering which notation system is which. Orbital notation is drawing the actual orbitals. So you have to draw the name of the orbital and the little line, and then your 2 electrons per orbital. So for 16, that gets you out to the 3 p's. And 3px, 3py, 3pz, 1, 2, 3, 4. Whoops, and I just did that illegally. 1, 2, 3, and come back to fill with a 4th. Okay, write the electron configuration for chlorine. So what you have to do is look at a periodic table and see how many electrons chlorine has, and this was sort of a gift because chlorine has 17, so basically you can take this that you did up here and add 1 to it, which sort of is a foreshadowing of something we'll start to do in the next chapter when you learn Rockstar shortcuts, so you never have to count electrons ever again. Yeah, you get through this and then you'll never have to do it again because you'll know how to look at the periodic table and say, oh, that's going to finish filling with 5d3. It's like a party trick for geeks. Your superpower. So on the second one, like I said, that was kind of a gimme. What element is represented by the electron configuration given here? 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. Well, none. Ha! I screwed up the question. If you just counted those up and added them up and you said, oh, 21 electrons, that's scandium. That's good. You are clever. You know the trick of just counting the electrons. However, if you actually looked at those, you realize that 4s2 was missing. And we can't fill in the 3D until we've filled 4s. So what this really should have been, if we put that 4s in there, that would be vanadium if we put that 4s2, those 2 electrons in there. Okay, show the electron configuration for an element with 37 electrons using both forms. What a pain in the tuchus that turns out to be. Here's the place where people had problems. If they were not drawing the subshell filling diagram correctly, then they don't get the order correct on this, because this gets you into the territory where you have things skipping. So you should be ending with a 5s1, and very often you can kind of shortcut it yourself and just look at what it ends with. And if you're ending with the same thing, then scan back. Do you have all the same subshells with the same numbers? And you shouldn't end up in the same place if you've not done your subshells correctly. So you should end up with a 5s1. And let me take a better picture that shows the... Okay. If we do this, you should be able to see we go from the 3p's to 4s, the 3d's. There are 5 3d orbitals. They each hold 2. So how many total electrons can you have on a d subshell? 10. Same number of fingers you got. 6 in the 4p subshell, and then 1 hanging out there alone in the 5s. So it's a 5s1. And I put here in this part of the answer 2 options because I honestly don't care if you reorder your subshells. I don't care if you go back and flip so that it goes 3p, 3d, 4s, 4p. I don't care. I tend to not do that. I certainly wouldn't ever do it when I was writing it because I will screw it up because I can't keep count, that way. Your book does reorder them, but I've never had a chemist say to me, "Oh, I can't believe that." Nobody cares. So it's what it ends with is the thing that really matters in terms of behavior. Okay, configuration for neon. This was pretty easy. We like things with 10 electrons. They're easy to write. And it's also nice, I think, to see the orbital notation with the electron configuration notation because it's a good reinforcer. And I see that a lot of you still do the orbital notation before you do electron configuration notation. That's fine. That's okay. Radon! Holy cow, what was I thinking? I didn't even finish the key. The bell rang, and the planning period was done, and I hadn't finished writing the orbital notation for radon. What kind of lunatic assigns the orbital notation for radon? Jeez Louise. Well, let's do it together, shall we? So good old radon. This is the radioactive toxic gas that leaks out of limestone topography into people's basements and gives them a higher incidence of lung cancer in some parts of the country. Naturally occurring, radioactive, noble gas. 86 electrons. So, to do 86 electrons, it is imperative that we have the correct subshell filling diagram. And I'm going to show you the problem that I'm seeing. Everybody gets to hear just fine. Not a problem. No issues. Below here, it gets a little bit funky. So, you know that you have a 5s, 5p, 5d, 5f. You don't have to go all the way out to the f's in 6 and 7, but you must go all the way down to 7 on your s's and p's. So, 6s, 6p, 6d. You can even, I think you can even usually stop there. And I'll show you why it matters. 7s, 7p, 7d. It matters because if we do these lovely little lines, and everybody's fine up to here, like I said. If you're starting at 4D, which we do plenty of things that go to 4D, that line goes through to 6S. If you didn't put 6S on there, you think that you go from 5P to 4F. And I had people who made that mistake because they didn't have the 6S there. So you gotta take those S's all the way through 7. You have to, because we actually will do a configuration for an element that is filling in the 7S subshell. You can roll your eyes all you want. They're big, they're funky, and they're radioactive. They're unstable. You know, do we go much above 7S? Not so much. And you'll start to see why when we do a really big one. But, you know, you can, if you're going to go to 5F, you got to go to 7P. So the easiest way to do it is to just make sure that you at least, I mean, and you can, whoops, wrong font there. You know, you can do your 7D, 6F, but you do have to go all the way down to 7 on your S's and P's at least. So let's shrink this and let's look at good old radon. What a booger. All right, so 1S, 2S, 2PX, 2PY, 2PZ. Zoop, 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 zoop. Let me pause this. Okay, so we've got our first 10 filled. We're up to 2PZ. What fills next? 3S. Okay, so we're going to put electrons in there. And that fills. And what fills after 3P? 4S. There she blows. So we have 4S, 1, 2. So we've got 2, 4, 6, 8, 10, 20, 2, 4, 6, 8, 10. So I've now got 20 electrons. Only 66 to go. All right, so what fills after 4S? 3D. 3D, 3D, 3D1, 3D2, 3D3, 3D4, 3D5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 more electrons down. And I'm stacking these. We usually don't do that. We usually try to write them all out in one line, but it's really tough when you have 86 electrons. What fills after 3D? 4P. There's our little 4P. So 4PX, 4PY, 4PZ, zoop, zoop, zoop. 1, 2, 3, 4, 5, 6. That's about as messy as you could make it. What fills after 4P? 5S. 5S, 1, 2. And I'm just going to kind of write a little tally for myself here. So that's 20, 2, 4, 6. That's 6 more. What fills after 5S? 4D. So 41, 42, 43, 45, can't count, 44, 45. Oh, you're right, it is. Thanks. 30 and then 6, so we're up to 36, and then 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's another 10. So now we're up to a total of 36, 46. I'll get rid of these. And I actually do, if I'm writing something that has a lot of electrons and I'm doing an orbital notation, I do make little marks to myself of how far I am. So I've got 46. What fills after 4D? 5P. 5PX, 5PY, 5PZ. Draw those out here. 1, 2, 3. 1, 2, 3, 4, 5, 6. I'm up to 52 now. What fills after 5P? 6S. 4, 6, 8. Oh, you know what? And that was 38, 2, 4, 6, 8. So I'm up to 48. Whoops, I just keep screwing up all over the place today. So now we're going to do 6S. 1, 2. Oops. Shrink it and move it in there. So I've got 48 plus 8, 54. But wait, is that 48? 38, 40. Yeah, 48. So we're up to 54 now. I'll get rid of this. 56. Can't do arithmetic. Not to save my life today. Okay, we're up to 56. Only 30 to go! This is awful. I'm going to shrink all of this because I can. If you were doing this on notebook paper, of course, you're just stuck. What fills after 6S? What? 4F. So we are jumping back. How many F orbitals are there? 7. So remember we had 1 S, 3 Ps, 5 Ds. We have 7 Fs. So we get 4F1, 4F2, 4F3, 4F4, 4F5. Why did I make that F a subscript? 4F6, 4F7. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 56 plus 14, 60, 70. Yeah. I'm going to shrink this. Only 16 to go. So we're up to 70. What fills next? 5D. Hey, lo and behold, guess what? 5D has how many? 10. Oh, we still need 16, huh? Darn it. 5D1, 5D2, 5D3, 5D4, 5D5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That gets us to 80. We need 6 more. Okay, now I can do my little lo and behold. So we're at 80. And next up is the 6p orbital. And how many is that going to get us? 6! Woohoo! 6px, 6py, 6pz. That was exhausting. 1, 2, 3, 4, 5, 6. So, as you can see, it's a pain in the tuchus. Huh? I'm glad you think so. I can give you lots for extra practice if you want it for your spare time. Like I said, next chapter, I'm going to teach you a trick that will allow you to look at radon and immediately write its configuration without counting anything. It's the coolest party trick ever. Now, one more, which was the subshell filling diagram, which I think we kind of covered when doing why it's important. So, if you had issues on the quiz, do you feel like you see where they were? A lot of you did really well, and the few of you who had some issues, I think they were pretty simple issues that can be addressed, for the most part, with doing a better job on the diagram. Yeah? Okay. We have 13 minutes. Okay. So, tell me this. What is a noble gas? What is a noble gas? Okay, I see the smarty pants. You're right. They're the elements. Okay, so yeah, noble gases are unreactive group 18 elements. Let's do something here real quick. We're gonna learn our first big shortcut for writing electron configurations, and it's called the noble gas notation. So far we've learned orbital notation, which is the giant pain in the butt where you have to write every single electron. Electron configuration notation, where you just say how many are in a subshell. And now we're going to shortcut it even more. So you're going to need your periodic table out. Okay. So the noble gases are stable because why? We just said full outer shell. Full, and it's actually full S&P. Full S&P. So let's go ahead and we'll do helium. Let's write the electron configuration for helium. It has 2 electrons. You can skip orbital notation altogether. Where are we filling? Where do we start? 1s. It's got 2 electrons. Hey, we're done. That was easy. I could do writing helium all day. So let's look at neon. Next one down. So we've moved down a group. And neon has 10 electrons. So this would be 1s2. 2s2, 2p, how many do we need? 6. And hey, looky there. There's that full S&P in the uppermost main occupied energy level. Cool. So, next on the hit parade is argon. Let's move these over. And argon has 18 electrons. Okay. 1s2, 2s2, 2p6. What comes after 2p? 3s. We still have, what, 8 to go? 3s2, what comes after 3s? 3p6. And hey, looky there, we're done. And lo and behold, full uppermost occupied main energy level. When we talk about uppermost occupied main energy level, that is the highest number that you see when writing the electron configurations. That is the highest occupied main energy level. It's the highest location where they have any electrons residing. And when we get into those crossovers, there are things that are higher energy, but are still a lower main energy level. A little bit complicated, but nothing you can't handle. Okay, starting to get ugly here, folks. We're going to go to krypton. Well, actually, you know what? Let's not. Let's just not go to krypton, shall we? It's not good for Superman. It's not good for us either. Oh, that's kryptonite. That would be the mineral made of krypton. I understand. I get that confused all the time. Let's just... You didn't get that? We can write these. Great. Fantastic, Moser. Okay, we see that they have a full S&P on the uppermost main energy level. Let's do a little experiment here, shall we? I'm going to select this. I'm going to switch over here, and I want to look at these first couple of columns. I want to look at group 1 and group 2. So this is now a meaningless reference. There is no more noble gases sitting there. I suppose I could have copied it instead. Well, let's write the noble gas, or let's write the electron configuration for sodium. I'm going to shrink this up a little bit more. So sodium, good old sodium. Do you want salt on those fries? Nah. 11 electrons. You won't forget it. So 1s2, 2s2, 2p6. Where do we go next? 3s1. Well, look at that. 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. All sodium is neon plus an electron. You think you're so tough. You're just neon plus an electron. We take advantage of this fact, and we use what's called noble gas notation. And in noble gas notation, we can say, hey, whatever this element is that we're referring to, it is exactly like this one plus that. So when we put that neon in that squared off bracket, we're saying it's got everything neon has plus a 3s1. A lot easier, isn't it? A lot less writing. We're going to practice a few of these. Okay, so let's explore our new trick, shall we? So we did the notation for neon and followed it up with sodium. And we said, hey, sodium has everything neon does plus 1. Cool. Well, note that what you're really doing is going up to the row above your element and going to the noble gas there. That's the rule. So, you care to take a wild guess without counting electrons or doing anything else? What noble gas would you use to write the noble gas notation for cobalt? Argon. Because you're going up one row to the noble gas. Oh, cool. What noble gas would you use to write the notation for boron? Helium. Pretty boring. You don't get a whole lot out of helium. It takes almost as much to write brackets He as it does to write 1s2, but it's an option that exists. Okay, so let's practice. Let's explore the practical implications thereof. Get rid of all that. Select this and shrink it. And we're going to do silicon. Atomic number 14, 14 electrons. So, if we're writing the electron configuration for silicon, and we are going to do it in noble gas notation, what noble gas are we going to use? Neon. So we're going to write Ne in brackets. And how many electrons beyond what neon has does silicon have? 4. And hey, look at this. This is weird. Here's neon. And if I go 1, 2, 3, 4. Huh. Interesting. We'll explore that more next chapter. Okay, so neon, we remember, ended with a 2p6. What fills after 2p6? 3s. And we've got 4, so we know that 3s is full. And then we got 3p, how many? 2. That's silicone, written the short way. Ooh. Here's one more trick I'm going to show you. And this is again a foreshadowing to what we'll do in the next chapter. If we take that periodic table, and we can't remember off the top of our head, because the noble gas shortcut does you no good if you have to write out the noble gas to remember what the noble gas filled with, does it? So remember how I said they always end with an S and a P, full? Well, this one, helium, ends with a 1s, 2. This one ends with 2s2, 2p6. This ends with 3s2, 3p6. Anybody care to guess what krypton ends with? 4s2, 4p6. You want to make a wild stab guess at xenon? 5s2, 5p6. Guess what radon ends with? Oh, you just did this on the quiz. 6s2, 6p6. So when you do a noble gas notation, you can look at these and count and know exactly where that noble gas ended and where you need to pick up. So when you have your subshell filling diagram handy, 1s, 2s, 2p, whoops, 3s, 3p, 3d. I'm doing this too messy. So we're going to do selenium, atomic number 34. What noble, and I'll let you go ahead and get started. Argon, 4s2, 3d10, 4p4. How many of you have that exactly? Okay. Some of you are still working? I'm sorry. I'll shut up. Okay. Do you want to do one more together, or do you just want to be turned loose to practice? One more? Okay. Let's walk through it let's walk through the solution to this one first. So, I know, because selenium is here, that I'm going to use argon as my noble gas. Good with that? Okay. I know that argon ends at a 3p6. So now I'm going to look at my filling diagram and say, well, if I ended on 3p, what do I fill next? Well, I fill 4s. And how many more electrons do I need? Well, 34 minus 18, I need 16 more electrons. So I know I've got 2. After 4s, what do I fill? Why, I fill 3d. That gets me 10. I now have 12. I need 4 more. What fills after 3d? 4p. And there's my last 4. So, you good with that? Do you want to do one more together? Or does that make it... Let's do just one more together, just in case. Okay, we're going to do cadmium, atomic number 48. So, you all know how to figure out which noble gas you're using. Okay, so I know that krypton ended with what? Let's see, 1, 2, 3, aha. This ended with a 4s2, 4p6. So what starts to fill after 4p6? 5s. And how many electrons do I need to get from krypton to cadmium? Well, 48 minus 36. So I need, this is basically krypton plus 12 electrons. Okay. So, krypton. Well, I get 2 there, 5s2. And what fills after 5s2? 4d. And so 4d is going to get me, oh, well, it's going to get me the remaining 10 that I need. Does that make sense? Okay, I'm going to turn you loose to practice.